We go. Let's go. Okay, another amount of substance. We got M as a group 2 metal that forms a nitrate MnO3 The NO3 is in brackets with a 2 outside. 0.320 grams of N nitrate. Metal nitrate is heated strongly and decomposes completely. The mixture of gases formed has a volume of 225 centimeter cubed at 450 degrees and 101,000 pascals. Determine the MR of M from the metal nitrate. Identify M. Well, we know because we've been given R is 8.31, we need to use PV equals nRT. We're looking to find the MR, so we need N so that it can go in our MR and mass equation. So we're going to do PV over RT equals N. We know the pressure is 101,000. They've given that to us nicely in pascals. We've been given the volume, but you must convert to meters cubed in these ideal gas equations. You can do that two ways. You can do 225 times 1 times 10 to the minus 6, or you can divide by 1 times 10 to the 6, both the same. Now that's going to be divided by 8.31, the gas constant, times 450 degrees, but turn it into Kelvin for this, so add 273. Now you've done that, you'll have scored for the rearrangement, you'll have got a mark. For the correct conversions, you'll have got a mark. So you'll be on at least 2 marks here. Now we're going to get 3.78 times 10 to the minus 3 moles, but remember that's of our gas mixture, okay? Now we need to use the ratio from the equation. Now if we look at the ratio in the equation, we've got 4 nitrate gas molecules and 1 oxygen gas molecule. That's a total of 5 moles. So that's a ratio of 5 moles of gas to 2 moles of the metal nitrate. So what we're going to do is we're going to times 3.78 times 10 to the minus 3 by 2 divided by 5, right? And that is going to give us the amount of moles of metal nitrate. Now, if you don't really understand that, you could say, right, let me work out the moles of oxygen. And you could say, I'm going to divide 3.78 times 10 to the minus 3 by 5 to find out how much 1 oxygen mole is. And then I'm going to times it by 2 because it's in a 1 to 2 ratio with the metal nitrate. So you could do it that way as well. Now that we know our moles of the metal nitrate is 0.001512, what we can do is stick it in the mass over ml times moles. So we're going to have 0.320 grams over the top of 0.001512 mole. So what we've calculated here is that the MR of MnO3 is 211.6 is the MR. So if we want to find M, we need to subtract NO3, which is 14 plus 48 times 2. We need to subtract that, which is total 124, from the 211.6, which is the full formula's MR. And if we do that, we'll find out the MR of the metal M. And then we just need to look it up in the periodic table and identify the metal. And so we can see with an MR of 87.6, if we look here in group 2 of the periodic table, you'll find strontium is your unidentified metal. So there we go. Boom. Now let's move on. Oh my gosh, this question is about a volatile liquid A. This is question 8. This question is about volatile liquid A. 8.1, a student does an experiment to determine the relative molecular mass, the MR, of liquid A using the apparatus shown in figure 0.2 down here. The student injects a sample of A into a gas syringe into an oven. At the temperature of the oven, liquid A vaporizes. Calculate the MR of A. Give your answer to 3 significant figures. Always remember that, guys. So many people lose a mark there. We have the gas constant, 8.31. Joule K mole to the minus 1. Listen, we know when we've got that, we're looking at the ideal gas equation. They've been talking about gases, gas syringe, vaporize, and then we look at the data they've given us. We've got pressure, we've got the ideal gas equation. So you should remember that PV equals nRT. Now, they want us to calculate MR. That is the focus. In order to calculate the MR, I need to find moles. So I need to rearrange this equation to make moles the subject. So we're looking at PV over RT. You're going to divide PV by RT, and that's going to leave you with moles on its own. And that's what we need to get down to. Now it's all about converting these units up here. The grams we can leave till we have the moles, and then we whack that in to find the MR. But let's get down to the rest of it. So pressure. What have we got? 100 kilopascals. Now, you must learn this off by heart, of course, all these situations, practice, practice, practice. 100,000, we need to use pascals in this question for pressure, not kilopascals. Now we're going to multiply that by the volume. The volume is in meters cubed. What is the volume? 0 before, 178 after. So I need to do 178, and I want to divide that, we're putting this into meters cubed, by 1 times 10 to the 6. Okay, why do I want to do that? Well, we need to put it into meters cubed, and there are 1,000,000 centimeters cubed in 1 meter cubed. So I'm dividing by 1,000,000. Now, the next little thing that we've got to do over here is come up with the temperature of the oven is 120. We need to convert that into Kelvin. So 120 in Kelvin. 273 plus 100 is 373 plus 20 is 393. Sorry, it took a while for my brain to work there. And of course, what is R? Doing it in a backwards order. What is R? R is 8.31. Whack this all into the calculator. And we get N, which is our moles, is equal to 5.45 times 10 to the minus 3, or 0.00545. Now, that's our moles. How do we now need to rearrange this equation, which I'm whacking over here, moles over mass. Oh, gosh. I do not know what I am doing. Right, let's do this. That is the most bent diagram ever. Okay, mass, MR, and moles. Good to remember that. Mass over moles equals MR. So we want to find the mass. We have the mass before injection, the mass after injection. Let's whack that in. So we've got 11 point, we can just do 11.295 in your calculator, subtract 10.835, smash that over the top of the MR, the moles, which was 5.45 times 10 to the minus 3. Oh my gosh. And that is going to give us our lovely jubbly MR, roughly 84.4. Remember 3 significant figures, and that is our MR. 5 marks. Boom! Or 4 marks. Yeah. Okay. The student noticed that some of the liquid injected into the gas syringe did not vaporize. Explain the effect this had on the MR. Well, basically, you're going to have lower volume, right? Which is going to give you lower moles. Because you've got lower moles, you're going to do mass divided by moles. As the N is smaller, we get a greater MR than expected. Nice. So you get a smaller volume because less is vaporized. So smaller volume, that's your P times V is smaller, which means that when we do PV over RT, we get a smaller N, which is the moles. And then when we do mass over N, we get a greater answer because the N at the bottom is smaller in that equation. So our MR is greater than expected. And that's a very common question on these. So each reading on the balance used to record the mass of the fine needle syringe and contents had an uncertainty of plus 0.001 grams. Calculate the percentage uncertainty in the mass of the liquid A injected in this experiment. So it says each reading on the balance, and we've got 2 readings on the balance. So we need to do 2 times 0.001. Percentage uncertainty is where you divide the uncertainty, the total uncertainty, so we're doubling that because there's 2 readings, over our reading. So what was our reading? Our reading was 0.460, and you get that from doing the final mass, take away the initial mass, and there we go, times 100. Percentage uncertainty is 0.35%. Lovely jubbly.
At a different temperature, a mixture contains 0.025 moles of sulfur dioxide, 0.049 moles of oxygen, and 0.034 moles of sulfur trioxide. Total pressure of the mixture is in a 3,500 centimeter reaction vessel is 255 kPa. Use the data to calculate the temperature in degrees of the mixture. Ideal gas constant 8.31. So we're going to use the ideal gas equation here, rearrange it to isolate T, the temperature. You do that by dividing PV by NR, then you move those out of the way. And it's literally, these are 3 marks, I think, of these. These are straight conversions. So what's the pressure? Well, pressure should be in pascals, not kilopascals, so 255,000. Then we need to straight convert the volume. Volume needs to be in meters cubed. So we need to go 3,500 and we need to divide it by 1 million centimeters, or 1 times 10 to the 6. And that gives us our volume, which is 0.0035 meter cubed. Now we don't need to convert R, it's just 8.31. We need to know the moles. And the moles is going to be the sum of all the moles in the mixture. So add all the moles in the mixture up, and you get 0.108 moles. Plug it all in by doing 255,000 multiplied by 0.0035 meters cubed, which is the volume. Make sure you put brackets for all of this, otherwise it won't come out good in your calculator. And then divide it by the moles, which is 0.108, times by 8.31. Again, you should bracket that. And that's going to equal 994.5 Kelvin. Now what we need to do is subtract 273, because the answer they want in degrees, and that equals 721. We can get rid of the 0.5 because we put it to 3 significant figures, which is kind of standard at A level. And that's a lovely question for picking up marks. Practice, practice, practice is the way that you get good at chemistry A level. Once you've got these techniques down, these are like 3 marks.
Question 5. Okay, let's get into this one. So this says figure 2, question 5 represents 2 glass flasks, P and Q. There's P, there's Q, there's a little tap in between. Connected via a tap, yep. Flask Q has a volume of 1 times 10 to the 3. It's filled with ammonia, NH3, at 102 kPa and 300 K. The tap is closed and there is a vacuum in flask P. Gas constant 8.31. There's a lot of information to dissect here, but essentially, immediately, what should your brain be thinking of? Which equations should spring to your mind that are going to come up in question 5? They're giving us the molecular, well, they're giving us a volume here, and they're giving us pressure, and they're giving us the gas constant. You pretty much know you're going to do PV equals nRT. So if you haven't memorized that, slap yourself in the face, because you need to memorize that. And then they've also given us Kelvin, so that's confirmation. They're giving us the molecular formula, so that means we can work out the MR, can't we, of ammonia there, because 14 plus 3 is 17 MR. So you've basically been given the MR, so we could be doing mass over moles and MR. So yeah, we've been given lots of info here. Let's go down and see what the actual question is. But whenever I read a STEM, before I've read the question, I like to test myself. You should get in the habit of this. Test yourself and have a guess of what you think might be coming up. Because if you get your brain into that way of thinking all the time when you're reading the STEM of a question, oh, I think they're going to ask me about this equation or that equation. That is how you know you're developing the skills to be an A-star student. Okay, calculate the mass of ammonia in flask Q. Give your answer to the appropriate number of significant figures. So immediately there, we know that we're looking at what we were talking about, mass over mR times moles. We also know that we needed PV equals nRT. What's the connecting factor between these 2 equations? It's the moles. So I want to start off by rearranging this PV equals nRT so that I have PV over RT equals moles. Once we have the moles, remember we had the MR of NH3. We were given NH3 in the stem of the question. Then I can do NH3 times N, and I can get the mass and then put it to 3 sig fig. And boom, you've got your 3 marks. Why don't you pause the video, have a go, and then unpause and check off your answer. So we need to look at what our pressure is in, because it should be in pascals. We've been given 102, so that's 102,000 pascals. 300K is cool, 8.31 is cool, and we got a volume of 1 times 10 to the 3. But what are we being asked about? Yeah, 1 times 10 to the 3. Okay, so let's get into this. So we want pressure, which was 102,000, times our volume, which is 1 times 10 to the 3. Now, this was in centimeters. We have to convert to meters cubed. So what I want to do now, what you can do is you can times this by 1 times 10 to the minus 6 to change into meters cubed. You can divide it by 1 times 10 to the 6, divide it by a million, because there's a million centimeter cubed inside 1 meter cubed. So you can divide by a million, but that's equivalent to timesing by 10 to the minus 6. Now I have 8.31 for R, and I have 300 for the temperature. Sometimes they give that to you in degrees. Just add 273 to change to Kelvin. And then what we want to do is work out what the moles are. And the moles work out as 0.040, something like 91, whatever. You could keep writing and writing, but you keep it in your calculator. We're now going to take this over and multiply this by the MR. Now, the MR of ammonia, N is 14, hydrogen is 1, and obviously NH3, therefore I've got 3 hydrogens, so my MR is 17. So let's times 0.04091 by 17, and I get 0.04091 times 17. What do I get? I get like 0.695. I'm going to round that up to, I got like 0.695 something. I'm going to round it up to 0.696 grams and round that to 3 significant figures. So that is what I am giving it there. And that's going to get you 3 marks. So really 1 mark for all your conversions and putting that in the equation, getting the MR, timesing it by that, coming up with the 3 sig. There we go. Right. Let's zing down to the next question. And it's probably going to be another one. Yes, it is, to do with this flask situation. 5.2. When the tap is opened, right, they've opened the tap in the middle between Q and P, the 2 bits to the flask. Ammonia passes into the flask, P. The temperature decreases by 5 degrees. Okay, so we've gone from 300 Kelvin minus 5 degrees. The final pressure in both flasks is 75 kilopascals. We know the pressure again. Calculate the volume in centimeter cubed of flask P. Guess what? We're doing a PV equals nRT again, but this time we want to calculate the volume. So let's rearrange PV equals nRT. How would you rearrange that to find volume? Well, divide both sides by P, and I'm going to end up with N times R times T divided by P equals volume. Now, what's beautiful here is we already worked out the N. I believe it was 0.04091 from the last question. So I want to do 0.0. Oh, was it 0.0 or was it 0.4091? Let me double check. Yeah. 0.04091. It might not have been exactly that. So it might be 0.041. Maybe I should just round it to 0.041, but there we go. Probably better to do that. Times 8.31. Now you might think, hold on, if I've got 300K, this might confuse some people. So I just want to minus 5 degrees. 1 degree is equivalent to 1K, so that just equals 295K. So that's now going to be times 295. So that's just testing you on that concept. You might think, oh, have I got to do minus 27? No. Each one rise in 1 Kelvin is the same as 1 rise in 1 degree. They just have a different starting point, which is why we use different numbers for them. Now it's 75,000 this time because we use pascals. And if we do that, we're going to get the volume. But bear in mind, the volume we calculate is in meters cubed and they want our volume in centimeter cubed. So let's zing, zing, zing this. So let's do this, smash this in the calculator, and I get 1.34 times 10 to the minus 3. So I think that's going to have got us 2 marks already. One for that. Okay, let's say that's got us 2 marks. Excuse me while I have a sip of coffee. Okay, so what we're going to do now, and probably this is the hardest bit. Where am I? No, not yet. Right, we need to put that into centimeter cubed. So I need to times this by, that's meters cubed. So I want to times this by what? 1 times 10 to the power of 6. Times it by a million. Do you remember I said there's a million centimeter cubed in each meter cubed? Then we're going to get a total volume of 1,340 centimeter cubed. Now, this might be different in your calculator slightly because your moles here, I did a stupid rounding there, so yours might be slightly different. So I've got 1,340 centimeter cubed. However, there's a little trick here, and this is the difficult bit, really. To get this last step is very hard. If we come back up and look at the flask, I've got all my writing all over the place. So let me just delete all my writing. Right, if we look at the flasks, we open the tap. All of this information, the new information we've been given down below, is about both flasks. So what I need to do, we've been asked just for the volume of P. Now, obviously, the volume of P is smaller, but we've been told the volume is 1 times 10 to the 3. So for Q. So I need to take our new volume, which works out to be the volume for both flasks, because we used the pressure and we used everything, the moles of both. So I need to put this all back. How do I do that? Yeah, there we go. We're back, right? And then this is the volume for both flasks. The pressure was the same in both, 75,000. The temperature's the same in both. The amount of moles of ammonia are the same in both. So technically all of these were for both. So we've worked out the volume of both, but we know that this is P plus Q. And if I want to find out P, I need to do P plus Q minus Q equals P. So P plus Q minus, and Q was 1 times 10 to the 3, which is 1,000 centimeters. So my P is going to equal 340 centimeters, there or thereabouts. Now, I'm not saying in the mark scheme, it might be like 337, 336. It could be slightly different to that. I haven't checked the mark scheme, but I would imagine,
You're still here? It's over.